First of all, thank you very much for the invitation, giving me a short talk. Today, I will present you and talk about the quantum nature of the electron transfer or charge transfer in the biological systems, which is I use a bacterial reaction center and via density function theory, and especially with the range separated hybrid functionals. Now you're seeing the very large complex molecular structure, and as we know, this is a bacterial center is consists of very important pigments called chlorophyll, which is actually we might remember from the biology lessons, and this is responsible for the charge absorption of the sunlight, and then generation of the electron charge, and then sent to the cells, and then this process leads to the absorption of the carbon monoxide and finally release the oxygen for our human life. And I want to show you how this is happening in the complex structure. In the top of this bacterial center, there are some complex antennas. They play as a role antenna. They absorb light. The energy goes down to one of the pigments called bacterial phytin. We call it HA. A means on the left side a branch A. B means on the right side is a branch B. And this energy, which is actually extone decaying, like a leather vise, goes to the back to the BA, and this happening in same way on the right side, the energy transfer to the HB, and from the energy transfer to the BB, and finally the special pair, which is consists of a dimer of bacterial chlorophyll, and the special pair absorb this the energy and the electron. Now I'm changing my pointers, and the special pairs absorb the energy and excite an electron on the top. And now this electron choose the way the higher dielectric environment, which is on the A branch. So the electron goes back to the backward again to the BA, then HA, then QA pigment, and this goes to the QB, and finally it goes to the other part of the cells, and then the electron used by other environments to absorb to carbon monoxide and finally release the oxygen. And now we are working on this bacterial center. As you see, it's so many pigments and water molecules. You see the red points, actually oxygen. They are not hydrogen. They are actually water molecule indeed. And so far we try to understand the mechanism of this electron transfer, which is happening naturally on the plants. Any plant that is photosynthesis is happening. I will show you the spectral analysis of these pigments and rectification of the charge transfer inside this special pair. And there are, of course, remaining projects, the electron transfer of outside the special pair from P to BA and BA to HA. And we have also other projects going on, embedding potential that is take account to QM, and also energy transfer on the photoinactive side, which is happening to this site. Okay, what is the theoretical and computational protocol is? We are using here range separation hybrid functions, and especially we are using screened type of range separated functional, and for the electron coupling we are using multi-state fragment charge difference method, And for the environment, which is very important, we have a approximation, plausible continuum model, which generate the point charges around the core molecule that you want to study, and geometry optimization at the dispersion corrected omega evidence xt functional, and finally we calculate the rates using semi-classical Marcus rates and fully quantum mechanical based Fermi-Golden rule. And by the way, in this year, Rudolf Marcus has a 65 years old celebration. That's why some journal having a special issue about him. And we apply this theoretical and computational protocol on the only for this bacterial center as other organic molecules. But okay, I would like to give you some brief summary of the what is the SRSH. As you see, the equation 1 here, it shows a general expression of the column interactions, and this is a RSH type the definition of the column interactions. And here the as we know, Hilbert functions it combined semi-local density function, also as well as also the exact exchange interactions. So that's why it's called hybrid functional. And how to separate this the amount of the how much hybrid functional short exact exchange or DFT part is it can be used is defined by the omega parameter, and this omega parameter is can be tuned by relying on the Kopman's theorem by looking at the minima of this this G2 scheme. So when you tune the omega, you're looking the what omega gives to this the equation 3 close to 0 or very at the minima. Equation 2 is showing that general expression of the energy expression for SRSH. We have here alpha shows that it's the alpha determines the fraction of the Fock exchange in short range. Alpha plus beta is the long range exact exchange contribution in the long range, and this alpha beta is kept as 1 by epsilon, and we found that this using this convention and it represents condensed phase environment very well. So let's talk about the several success of the this scheme. And as we know, the RSH type functional, it's good to use for obtaining the accurate or more reasonable homolumo gap, a band gap for the condensed phase, also the big biological molecules. And here, from my previous group member, it shows already the how succeed the success of the as functional. And on the figure 3, it shows the IP and calculated homo of the single molecules. And you see the conventional RSH functional is very well represented by the RSH functional, and very good overlap the experimental values. And on the figure 4, now we turn to the SRSH PCM, and it's showing the success of the SRSH and OT SRSH, and well shown here with the small molecules, also in thin films. It's like C60, like a strong acceptor molecules and others. This is a HOMO and IP energies. And what is important to use of the SRSH scheme is if you want to look at the rate calculation of the or charge transfer of the biological molecule, you have to have the DFT function that has to define the charge transfer states. charge transfer state should be localized below the excited bright state, that is actually oscillating state, that absorbs the electron, and the electron goes to the next city state. We can call this the reactant state to product states. So, and figure 5 also shows this new scheme, a benchmark calculation of the SRSH and OTSS, very well presented with this functional. And okay, in 2018, there was an experiment, and they used the first time, as I remember, two-dimensional spectroscopy, and they are finally able to show one of the dark states that is actually was the mystery in the history. This is dark states of the special pair, and why it was a mystery in the literature, because if you look at this P plus star, actually it's the exact state of the special pair here on the purple bacteria it's called P, and because it's a low intensity, but also the absorption band is very overlapping close to the other adjacent molecules BA and BB on the left and right side. That's why so far some of the most of the experimental studies could not spot this the energy band, the peak. But recently this Niat-Ricos, actually this is the Jennifer Ogilvie group in the Michigan, they showed, and we also found this.
Your time is up, so you have to sum up. Your 12 minutes are done. So please conclude.
It's already, sorry. So we are able to show this P plus, and this is experimental shift that it's found in experiment. We were scanning the dielectric dependency for the special pair, and we have looked at exactly of the special pair, and we found a very meaningful result, that is the shift of the S1 and S2 is found experimentally 0.08 EV. Sorry, I have to show this. Here, this is experimental found a shift. We also found this experimental shift around this dielectric 1.6 and 1.8. And usually, we know that actually special pair dot envelope is in around 2. So this kind of show a success of the screened SRSH functional. And then we also studied each pigment.
You have to sum up. So please conclude.
Right.
You have to.
Right. We also actually I have a few more, but I think I cannot really.
No, you cannot. You cannot.
Right. Yeah, that's why it's so short. So we were also able to show the spectral shift on the BA, BB, and HABB, and the leading lines shows to the different dielectric results. And we later studied charge transfer state in the special pair. Is the mechanism of the electron transfer in the special pair, and we have a look to exact state of the special pair, and we see the localization of the city state below the bright state, and then we finally calculate the rate, which is consistent with the experimental finding, which says the electron goes from the PA to PB plus, which is dark state actually indeed. So I can just summarize as this. I think the time was really short for this presentation.
Yes, I think we will have to end here. Your 15-minute.
Right. It was yeah.
There is a very tiny question, but we are already use the 15 minutes. So any questions on the chat? I don't see any. No, in that case, please unshare your screen.
Okay.
Mute your
Thank you very
mic.
much for everybody for listening.
Okay. Thank you.